We have been for many classes now. In this class also we will continue discussing the same topic. So far we have covered all the memoryless modulation schemes we wanted to discuss in this course, and we have also qualitatively discussed the relative benefits of different modulation schemes and their decoding techniques. We have discussed also the generic decoding technique for any modulation, any signal set, and before going to the modulation schemes with memory, in this class and in the next class we will discuss some other topics related to memoryless modulation schemes themselves. One most important thing is the analysis of probability of error for a given signal set. That also we will discuss before we go to modulation schemes with memory. In this class we will start with what is called eye diagram, where we can see on an oscilloscope how much interference is there between, how much intersymbol interference is there in a qualitative way. So, we will now start discussing eye diagram. We have seen that for a pulse amplitude modulation system, baseband pulse amplitude modulation system, there is first a pulse PT which is fixed at the transmitter side, then it goes through the channel, and then at last it goes through the receiver filter at the receiver. And when the pulse PT goes through all these filters, first the channel filter and then the receiver filter, it undergoes some change due to convolution with the channel impulse response and the receiver filter impulse response. So the diagram we had is this. This is the channel filter. We are not considering the noise which would have come here after channel filter, and then it goes through the receive filter. This is CT, this is AT. So we call this P2T and this as P3T. Now we have also discussed the condition to have 0 ISI. What is the condition on P3 to have 0 ISI? That was given by Nyquist criteria. And now the problem is that we cannot always satisfy Nyquist criteria. We cannot, first of all, the channel is not in our control. Channel is not in our control, it is given to us. Only thing we can change is PT and AT. So PT and AT can be designed, but not the channel. Now, of course, we will always try to design PT and AT such that the pulse P3T, which is the convolution of PT with CT and AT, satisfies Nyquist criteria. That will avoid ISI completely. But it is not always possible to avoid ISI completely, that is, it is not always possible to design AT and PT in such a way that the pulse P3T will satisfy the Nyquist criteria. Because first of all the channel may not be known at the time of design of the filter. So channel, first reason is that channel. So this is why 0 ISI not possible always. That is because First of all, the channel may not be known, at the time of design. Secondly, it may be too expensive to implement PT and AT, which will avoid ISI completely. So, it may be expensive, too expensive to implement PT, AT to avoid ISI completely. So, we can design PT and AT to which will avoid ISI completely, but it may be that the designed PT and AT are too difficult to implement. In that situation, we would like to go for a suboptimal PT and AT, which will have some ISI, but which will not hopefully result in too much ISI. So, now once we have a PT and AT, how do we know in practice how much intersymbol interference is there? First of all, the channel may change. So, as channel is changing, is there a way of observing how the ISI is at any time? Like the channel may change, for example, for wireless channel which is continuously changing. If we go in a car or in a train, if it moves very fast, if you move very fast, the environment around is changing, and as a result the wireless channel is changing. So, in that situation, can we observe how much ISI my communication system is facing? So, that can be, so I diagram is a solution to that. I diagram is a graphical illustration of ISI. How do we get that? It is a graphical illustration which will give us some impression about how much ISI is there. So, how do we get ISI? Simply taking the output of the receive filter. So, we will not transmit only PT, we will transmit the summation AI PT minus IT, that summation, that is the many symbols. We was transmitting symbols after symbols, symbol after symbol, and we will receive some signal here. So, that is YT. Noise will also be there. Now, we simply try to see YT on an oscilloscope with symbol timing as trigger. So, we will have some transmitted signal xt. This is AK P t minus kt, k equal to 0 to infinity or minus infinity to infinity, and then we will have yt, which is the output of the receive filter, and then we will pass that output, we will observe that output on oscilloscope. So, this is observed on oscilloscope with, so we should have some synchronization to view anything which will make sense. So, oscilloscope with symbol timing as trigger. So, we will take the signal, we will generate a trigger based on from that, which will synchronize with the symbol timing. So, once we have a trigger which will synchronize with the symbol timing, we can give that on x and the yt in the y signal of the oscilloscope. then we will see one or few symbols on the oscilloscope. So, how will it look like? Let us say we have a binary PAM system. If you have a binary PAM system, suppose the pulse is after it goes through the channel and the receiver filter, suppose the pulse is like this, say like this, then we will observe a on the oscilloscope we will observe a signal like this. We will have this kind of view on the oscilloscope. Why is that? Because suppose the amplitude here is 0, that is amplitude here is minus and this is plus, then we have a minus pulse here, but it is going to plus pulse here. So, this is the symbol, one symbol interval starts from here and ends here. So, this is one symbol interval, and if it is 1 here, it will not be a rectangular pulse like this, but it will be something like this, and if it is going from negative to positive, it will follow this, because it is negative, it will have some inertia and it will go like this and go here, but even if it is 0 in the next symbol interval, it will go slowly to 0 here. So, if for example here also it came from 1 to 0, it would have come this way and then it would go this way and then again it will go back to negative. But if it was say 1 here also and 1 here, in the previous symbol also it was 1, then it would have come this way like it has come here. If it is 1 here in this symbol and in this symbol also, then it will go this way and then it will go to if it is minus in both the symbol intervals, then it will go here this way and then it will go up if the symbol here is positive, that is if it is 1. So, then it will traverse different routes to go to different states, either plus or minus. Remember, for 0 we assume that for 0 we will transmit this level, for 1 we will transmit this level, then it will go like this. So, if it is 0 for continuously 2 symbols or more, it will stay here in this, on this line, but not exactly on this line, it will do something like this, and if it wants to go back, it will then go this way. But if it comes this way and then immediately goes back, it will traverse a different route here. So, as a result, the line here will not be a single line, it will be a thick line, because many symbols are plotted at a time here, and at different symbols the lines here are different. So, we will have a thick line in between lines possibly here, and here also you can see that this is one line, this is another line, there may be other lines here. So, this is a type of plot we will see on the oscilloscope for binary PAM. And why is it called eye diagram? Because this looks like eye. And this, what is the use of this diagram? The use is that, now let us see how we do the detection at the receiver. How we do is, we know that this is the output of the matched filter, that is the receive filter, which is match filter is the optimum for receive filter, and we will then sample. So, these are the optimum sampling times. Optimum sampling times, because this is unperturbed by the neighboring symbols. You can see that here it is always a point, or more or less almost a point. So, if you sample somewhere else, if the value was minus here, that is 0 bit, then its value will go up if you sample somewhere else. So, this is the optimum point to sample here, here and so on. So, this need not be the exact symbol interval, but this length is the symbol time t, capital T, whether you consider it starting from here to here or here to here, this is t. Okay. Now, how do we know how much ISI is there? What is the immunity to noise? The immunity to noise is given by this gap, because as you can see that if these are large, then that is better, because then noise cannot bring this level to somewhere here. So that it will be negative. So, this is the 0 line, 0 volt line. So, this gap is most important for noise immunity. So, this A, the length A indicates noise immunity. Then this one, this gap indicates symbol timing error immunity. Suppose instead of sampling at these instances at the receiver, we sample here, here and then here and so on. That is, there is some offset. Our sampling clock is not completely synchronized with the symbol timing. So, we are sampling at the wrong instances, which are deviated from the optimum sampling instances. But how much error would we get due to that? That depends on this B, because as you can see, if this is B, if the error is B by 2, here it comes here, then sampling here you will not be able to judge at all anything about the bits, because they will be near 0 volt all the time, here, here. So, more this gap, the better for sampling time error immunity. So, B indicates sampling timing error, indicates immunity to sampling timing error, sampling timing error immunity. So, even if there is some missynchronization of the sampling clock and the symbol timing, if the B is large, we will not have too much problem. So, B gives some quantitative, in fact it is some quantitative measure of how immune the system is to sampling timing error, whereas A indicates the immunity to noise. How will, so this is for binary PM, how will the signal look like for 4 PM? So, then the signal will look like this. You will have more lines, there are 4 levels, this is one, this is another, this is another, this is another. So, there will be 4 levels, but there can be transition from any level to any other level, or any level to any level, from one symbol interval to another symbol interval. So, it may go from here to here, here to here, here to here, or here to here. Similarly, it can go to anywhere from here, and anywhere from here. So, and again just like binary, we will have many lines for each transition, because this one, if the previous symbol was also at this level, it will take a different path here. If it came from different level here, it will come again for it will go again in a different way, and so on. So, for binary there will be few, and for PAM also similarly there will be many lines from any state, any level to any level in the next interval. So, this will be the I diagram for 4 PAM. And again here, this is the this indicates the noise immunity, and this indicates the immunity to sampling time offset. So, we have discussed what is I diagram, and we have seen how I diagram looks like. I diagrams look like eyes anyway, and we have seen particularly how I diagrams look like for binary PAM and 4 PAM oscillations, and for binary PAM and 4 PAM signaling, and also we have seen how from the I diagram we can infer how much immunity is there against noise and also against sampling timing error. Now, we will discuss another concept, another topic which we discussed before also, but now we can see the implications or rather relevance of those topics now, that is different kind of channel models. Previously, we have discussed different kind of channel models. We have discussed, for example, discrete channel, where you have a discrete set of possible transmitted symbols and also discrete set of possible received symbols, and there are different transition probabilities for a particular channel. If you, for example, binary symmetric channel is the most simple example for that. 0 to 1 there is probability, 0 to 0 there is some probability of transition, and so on. And in general, we can have M array discrete channel, and also we have discussed different discrete time real channels, meaning by what is transmitted is a real number, what you receive is also a real number, but it is on discrete time. So, and the channel is also of course discrete time. Input, output and the channel both are all are discrete time. Now, all the practical channels, most of the practical channels are analog channels, meaning by we transmit some continuous time signal through the channel, we receive some continuous time signal from the channel. Such channels are called waveform channels also. But what is then what is the relevance of discrete time channel or even discrete channel? So, though there are implicitly discrete time channel or discrete channels, those channel models are also useful for even continuous time channels. So, let us see some examples. So, we have seen that a typical continuous time communication system, continuous time but digital communication system is of this type. You have some message which will take value from 0 to m minus 1, and then there is a mapper which will translate m to a vector in some capital N dimensional space. So, you have a mapper. Which gives x. This is the vector. So, this x may be x0, x1 and so on till xm minus 1. They are vectors. So, for 2 dimensional constellations like QAM, PSK, this will be a 2 dimensional vector. So, this may be one of the points from, so of the one of the points from here, 16 QAM constellation. So, for 0 we will suppose select this, then 1, for 1 we will select this and so on. So, that is the job of the mapper. For the bits, for the integers, it will give you a vector, and then the actual modulation, which is basically, which will convert this vector into an waveform. How? We have discussed it already. For QAM signal, for example, we will have two basis vectors, phi naught t and phi 1 t. One is cosine omega c t times something, and the other is sine omega c t times something. So, p t cos omega c t, and then p t sine omega c t. There is some scalar here. So, and once we get a vector like this, say x naught x1, then we will multiply x naught with this, x1 with this, and add those signals, then we will get one signal which is to be transmitted. So, that is the job of the modulation block. It will take this vector, it will take the linear combination appropriately, and then give a continuous time signal as output. Then it goes through channel. Then we do demodulation, which is basically matched filter banks. So, matched filters and samplers. So, what we are drawing is basically a matched filter receiver. Then, so this will give as output the received vector, the estimate of the vector which was transmitted here, some point say here, and then we have the detection. We discussed before that this will involve picking up the point from the constellation which is nearest to this vector. So, this is a vector y, this is a vector x, and here the signals are continuous time, here it is discrete time. So, this will give an estimate of the message m. Now, this is the overall block diagram of the communication system, and this channel is continuous time channel. Now, if we consider this whole thing as a channel, why do we need to do that? We need to do that for several reasons. One is that suppose these systems are already designed by someone, we cannot change these systems, we can only play with the other things. Then we cannot design these things, so we have to consider this whole block as a black box. Then we need a characterization of how this block behaves. So, that is like a channel to us. When I am going to design the system outside here and on this side here, all I can know about this is the overall response of this part as a black box. So, this is like a channel to me, and we need a model for this channel. I do not require the channel model for this, because I am not going to use this channel. I am going to consider this whole block as the channel. So, now what kind of channel is this? This is now a discrete time channel, but it is a vectored channel. We have also discussed a vector real discrete time channel. It is taking a real vector as input and real vector it is giving out as output. So, this is a real vector discrete time channel. We can still design the constellations. This is only modulation and this is basically demodulation, matched filters and samplers to get Y. So, this is the space is given, that is, suppose dimension is 2, then this the 2-dimensional plane is given. How you select the points is still up to us. It does not require any change inside this block. So, we can still design the constellation, but we have to design is on this 2-dimensional plane, because here there are only 2 basis vectors for this case. So, we can still we need not take 16 QAM, we can take 8 PSK, we can take any other constellation we want, which will have less probability of error ultimately. So, we can still design these things, and we can design M also. M also can be changed, M is not inside. So, we can consider this channel, and there are another reason for taking this as a channel is that we can modularize the design phase. First design the modulation, matched filter, sampler separately, and then, because it is easier to design anything in a modular way, design first this part in the best way you can, then design the other part in the best way you can, and so on. So, first design the modulation, the matched filter, etc., all the analog parts first, and then consider the whole block once you have designed as a real vector channel, and then consider this, then design the constellation, keeping in mind all the constants you have on the average energy, number of bits that is to be transmitted, that is rate, and so on. So, this is now once you have designed this also, detection, mapper, all this. Now, this whole thing can also be considered for same reasons as a single channel. This can be considered as a single channel. Now, what kind of channel is this? This is now a discrete channel. It is not only discrete time, but it takes as input also some discrete values. So, it is now a discrete memoryless if there is no ISI. If there is some ISI, it will have some memory. But let us consider that we have removed ISI completely, then discrete memoryless channel and M array. There are M possible values. Now, we have discussed the models of these channels before. Now, why would we do this? Combine these and consider it as a single channel, again for the same reasons that these may be designed already and we would like to design all the outside blocks. For example, now we may like to design error correcting coding block here and decoding block here. There will be still some error from here to here. This M estimate of M need not be same as this original M. So, sometimes there will be some error and we will like to avoid, or we will like to be able to correct some of the errors. And for that reason, we may need to do some error correcting codes on the transmitter side and some error correcting the decoding of the error correcting code at the receiver side. So, here we will have encoder, here we will have decoder. And the models we have discussed before are for the real vector channel. We have discussed these models. There is some noise component here. The noise processes are assumed to be independent, Gaussian, zero mean Gaussian, so these are the inputs, this is the channel, this is a vector channel. So, this is y0, y1, yn minus 1, x0, x1, xn minus 1. So, this is such a channel, this channel, because here we are giving x vector and here we are receiving y vector. So, x vector and y vector, and we have also discussed before that component wise y1 is x1 plus n1 and so on. Noise is being added. So, there is a noise vector which is being added to the transmitted vector, and then received vector is the result of that. Then we have also discussed the discrete memoryless channel model, M-array discrete memoryless channel model, where there are m possible values, transmitted values, and m possible received values, 0, 1, m minus 1, 0, 1, m minus 1, and there is some transition probability. So, there is some probability, and that we have to that can be possibly computed. If this can be, if it can be computed, we can have these probabilities. So, we have seen how in the light of modulation and demodulation, we have discussed how discrete memoryless channel and real vector discrete time channel are relevant channel models even for continuous time channels. If we consider the channel along with some transmitter blocks and receiver blocks as a single channel. Now, we discussed one block here which we have not discussed in detail. This is a mapper which maps m an integer to a vector here. Similarly, there is some detection is of course the minimum distance detection. So, this mapper, does it really matter? That we have to see. So, when we do the mapping, we are actually mapping some bit sequences to a vector. So, for PAM signal set, for example, so we are discussing mapper. For PAM signal set, we have this is 0, there are some points here, say 8 p.m. we want to transmit 3 bits. Then 3 bits to, so all 3 bits combinations have to be mapped to one of these points. That is the job of the mapper. So, how do we do that? We can do it anyway, but what is the purpose for doing in any particular way? So, what should we look for? What we should look for is that when at the receiver we make an error in detection of the estimating the point which was transmitted. If we make an error, there should not be too many errors in the bits. So, if we have some bits here, some 3 bits here, some 3 bits here, instead of we transmitted this and instead of receiving this we received this, then the number of bits that are different between these two should be minimal. If there are more, then there will be more bits of error in a single symbol error. Now, it is more likely to detect when you transmit a particular symbol, it is more likely to detect when there is an error to detect either of these neighbors. That is, those are the most likely points which can be confused with this point if the received point is somewhere in between. It is very unlikely, there is some probability, non-zero probability, but they are very small probability that if we transmit this, the received point will be somewhere here near the other points other than the neighbors. Most of the points will be near this itself, but sometimes they will be near this, and even with very less probability they will be with other points. So, when there is an error, most of the errors are because the points that are detected are the neighboring points, one of the neighboring points of the transmitted point. So, we should try to see that the difference of bits between the neighboring points is minimized. There should be very little difference between the neighboring points. So, this is one particular way of doing it. Just this is called gray coding. Take 001 here, then there should be 1 bit difference between these two, between any 2 consecutive points. Then there will be always only, most of the times there will be only 1 bit error when there is a symbol error. So, there is 1 bit difference here, then there is 1 bit difference here, and then here there is 1 bit difference here. Sorry, this is 1 1, this is 1 0. So, this is different from the usual encoding. Usually we have 0 0 0 0 0 1, then 0 1 0 and 0 1 1, but here we have said 0 1 1 and 0 1 0. Here difference of bits between any two neighboring points is only 1 bit. At a time only 1 bit is changing. From here again we have this point 0 1 0 1 1 0 1 1 1 1 0 1 1 0 0. You can see that at any step there is only difference of 1 bit. So, this is called gray code. This is a gray code is a way of mapping bit sequences into pattern vector points. So, as a result in this case what will happen is that if there is some error, most of the times the error will, one symbol error will result in 1 bit error. So, the probability of symbol error will be same as, almost same as probability of bit error for this kind of mapping. Now, for PSK also similar thing can be done, obviously, because we can, there is some sequence in this. Suppose we have 8 PSK, we can have 0 0 0 0 0 1 0 1 1 0 1 0, then 1 1 0 1 1 1 1 0 1 1 0 0. Again, most of the times if we transmit this, we will receive one of these points if there is some error. Most of the times we will receive this, then sometimes we will receive this, and probability of receiving other points will be very less. So, again this is the gray coding for 8 PSK signal set. Then let us see another. What about QM? Suppose we have 16 QM. This is not sequential. So, this is quite nice. Even though this is not sequential, all the neighboring points can be mapped in such a way that all the neighboring points have only difference of 1 bit. Suppose you have these points, we can assign bits this way. So, 16 QAM, so there will be 4 bits to each point, 0 0 0 0 0 0 0 1 0 0 1 1 0 0 1 0, then go this way 0 0 1 0, then 0 1 1 0, then 0 1 1 1 0 1 0 1 0 1 0 0, then again this way 1 1 0 0 1 1 0 1 1 1 1 1 1 1 1 0 1 0 1 0 1 0 1 1 1 0 0 1. This is the gray code for 16 QAM constellation. Again here you can see that not we have assigned the bit sequences in this order, but so we know that horizontally if we go to neighboring points from here, here or here, there will be 1 bit difference. Here to here this bit is different, second bit is different, here to here first bit is different. But what about vertically neighboring points? Suppose you have this, go vertically up, there is only 1 bit different, the third bit, come down, there is only 1 bit different, fourth bit. So, vertically also you can see that any two neighboring points have only 1 bit different. So, that is again nice, because that will ensure that whenever there is some error, there will be only 1 bit error. So, one symbol error will most of the times result in only one bit of error, because most of the times the error will come because if you transmit this, most of the times you will detect a neighboring point instead of that point. So, these 4 are the neighboring points, and there will be only 1 bit difference between these points. Even if you go to the diagonal point, there will be only 2 bits different, because there is 1 bit different from here to here, and here to here again another bit. So, again 2 bits different. So, this is a very nice mapping, because all the nearest points have only 1 bit different, and next nearest points have 2 bits different, and so on. So, that is a very nice property to have. So, this is gray coding. So, we have discussed now, after discussing eye diagram, we have discussed different the relevance of different channel models, especially only this M array discrete memoryless channel, and also real vector discrete time channel. So, those channels, how they are useful, how those models are useful even for continuous time channels, even in a digital communication system with continuous time channel. And then we have discussed what criteria we should use for designing a mapper. How do we map bit sequences to points in the vector space? So, criteria we said for that is to minimize the probability of bit error. So, there will be sometimes symbol error that does not depend on the mapper, but once the symbol is detected erroneously, can we keep the number of bits that are in error minimum? So, that is the purpose of designing mapper properly, and the best known mapper is the gray encoder, and there it is ensured that for PAM, PSK, and also for 2-dimensional QAM signals, it is ensured that the neighboring points have bit sequences which are different only in 1 bit. So, as a result, most of the time one symbol error will mean 1 bit error. So, instead of, for example, here instead of receiving this point, if we transmitted this point and detected this point at the receiver, instead of this bit sequence, we will take this bit sequence. So, there will be only 1 bit error, the last bit. So, this is about mapper. Now, we have discussed before qualitatively about probability of error, how probability of error will change. We have said that probability of error will change if you decrease the distance between points, because then there will be more chance of getting confused between the neighboring points. If they are very nearby and noise takes the transmitted point near the other points, then we will be confused more easily and detect and commit error more frequently, and as a result the probability of error will be more if you have the distance between the points less. And also we have said that if you want to, so there is some trade off between the bit rate you can transmit, the probability of error you can achieve, and the average energy you are transmitting. If you want to get one better, one of the others have to be sacrificed. For example, if you want to transmit less energy, you have to either decrease the number of bits, or you have to increase the probability of error, because if you want to decrease the average energy, you have to put all the points near origin, bring all the points near origin. But if you bring all the points near origin, the distance between them will decrease if you keep the number of points same. So, the probability of error will increase. But if you do not decrease the distance between them, you have to decrease the number of points. You have to take less number of points, and as a result your transmission rate will be less. If you had 16 points before, now if you have 4 points, instead of transmitting 4 bits per symbol, you are transmitting now 2 bits per symbol. As a result, we will be transmitting less bit rate than before. So, energy can be minimized at the compromising bit rate. Then we have also seen that energy can be minimized, reduced by compromising the probability of error. Similarly, if you want to do, if you want to say transmit more bits, then we have to add more points. So, either you add more points around far away from origin, as a result you increase the energy, but keeping the distance between the points same to keep the probability of error same. So, if you want to keep probability of error same, but try to increase the bit rate, then you have to increase the average transmitted energy. But if you want to keep the probability of error same, but if you want to keep the energy also same but increase the number of bits, then if you keep the probability of error, if you reduce the probability of error, then with the same energy you can transmit more bits. So, there are different trade-offs. You can improve one of them sacrificing other. But what about for FSK? For FSK you do not need to sacrifice on energy to increase number of points. You do not need to sacrifice on probability of error also, because as you add more and more dimensions, the distance between the points do not change. So, probability of error will not be increased much. But what we are sacrificing there, what we are compromising there is the bandwidth, which would not change if you keep the dimension fixed. But for FSK, PPM, all these orthogonal modulation schemes, you are increasing the dimension to accommodate more bits. So, as a result we are compromising on bandwidth. So, there is some trade off between all these four: bit rate, energy, average energy transmitted, probability of error, and the bandwidth. So, there is some trade off between bandwidth, average energy, bit rate, and probability of error. We will discuss this probability of error aspect in the next class. We will see for different modulation schemes how to compute the probability of error, or how to get an estimate or a lower bound or an upper bound of the probability of error. Now, all the topics which we have covered in this class can be again found in the all common digital modulation books, including ProKIS, or the eye diagrams can be started from ProKIS, or even better from Lee and Messerschmitt. Again, digital communication by Lee and Messerschmitt or ProKIS. So, in the next class we will discuss probability of error calculation for different signal set. Thank you.